Good afternoon, everybody. So welcome to the second season of the online seminar series, Machine Learning Needs Mathematical Optimization. As you know, we decided to come back after the summer, and we will be running this seminar until, say, mid-December. And this online seminar series will also include a young session where we will have also young speakers presenting their work in progress. But let me focus on the presentation today. Today, we are very honored to have Leo Liberti as our speaker. So as we all know, he's a full professor at the École Polytechnique. And in the past, he has held positions at IBM, Politecnico di Milano, Imperial College, to name a few. So he's a leading expert in global optimization, combinatorial optimization, and mixed integer nonlinear optimization. In terms of data science, Leo has contributed to natural language processing, but also distance geometry. And on the latter, he has an invited review in TOP, which is the Operations Research Journal from the Spanish Statistics and Operations Research Society. He is a key contributor to the use of optimization to address complex industrial systems, has more than 100 papers in academic journals in our field. To name a few, he has EJUR papers, mathematical programming, mathematics of operations research, but also in applied fields such as in energy. He's also very successful in fundraising, and the funding comes from the EU, for instance, an ITN where he collaborates with other universities in the MINOA project, but also national, public, and private funding. So for us, it's a great honor to have him today, opening our second season. So the floor is yours. We got more than 50 people in the audience, and yeah, they keep coming. So
thank you.
Thank
you, Dolores. The honor is mine, actually. Thank you very much for the invitation. I can't thank you enough also for the invitation to write a survey for TOP. That was a huge fun. I'm not going to talk about that today. Instead, today I'm going to talk about random projections in mathematical programming. Now, this is probably as close to both machine learning and optimization as distance geometry really is. But this time it's a different set of works, and I think it's probably even closer to optimization than distance geometry, in the sense that I am looking at how to reduce the size of mathematical programs and at the same time ensure that you find approximate optima. Okay, so this is the overall topic, and I've published 5 or 6 papers in this topic over the last few years, in fact, and this is probably the first time that I attempt to look back and see the whole host of things that I worked on during the last few years. All right, so this is joint work with Claudia D'Ambrosio, Benedetto Manca, Pierre-Louis Poirion, and Qi Wu. But in fact, the two most active people would be Pierre-Louis and Qi. All right. Oh, and by the way, there starts to be a literature apart from my own studies on optimization in the context of random projections, and much of it is actually due to the next ML Needs MO speaker, Coralia Curtis, who will talk next time. So if you're interested in these topics, and I don't know whether she'll talk about that, but in case she does, then she also has many things to say. Anyway, so let me introduce what random projections are. Then I'll talk about their direct application to data, which has been known for quite a number of years, and then I'll talk about the theoretical part of applying RPs, random projections, to formulations, and then I'll show some case studies. All right, so the gist of random projections is that you have a big blue matrix, okay, this one here, that is your data matrix. The columns are records, for example, and the rows would be features of the records. Okay, and you have to do something with this database. I don't know. You have to maybe cluster it or do something else. And in fact, it's too large in order to cluster it efficiently. So instead, what you want to do is you want to somehow lose some of the features, but you don't know which ones. Okay, because you don't know what the features actually are. So these random projections are a set of techniques that will help you do exactly that. And what they ensure while projecting, while reducing the dimensionality of the blue matrix, is a sort of approximate congruence. You can see what they kind of aim at ensuring. Okay, for any two columns AI and AJ, the two norm of the original columns, the two distance, the L2 distance of the original columns would be more or less the L2 distance of the projected columns. Okay, so let's see what the projection is like. You have to sample the green matrix, which is very short and very fat. Okay, so when you do the scalar, the inner products like this, okay, you end up with something like the black matrix, which has the same number of columns as the blue matrix. Okay, so each column still represents a record, but it has fewer rows. Okay, so you've compressed somehow the feature space. Now the fact, how do you make the green matrix? This is one way of making it. It's not the only way, but it's probably the most popular way. T be a K times M matrix, where every component is sampled from a normal distribution with mean 0 and standard deviation 1 over square root of K. And K is low. K is much lower than the number of columns. It's, let's say, logarithm of n. I'll be more precise in the next slide, in fact, well, in the next few slides. This guarantee, this sort of guarantee that I left informal for the time being, is guaranteed actually WAP. And what WAP means is with arbitrarily high probability. So this is a probability of a set of events depending on some parameter k, such that as k increases, the probability of k happening increases, approaches 1 exponentially fast, as in this curve that you can see here. Okay, so it suffices to have moderate to low values of k to ensure that these EK events actually do happen. All right. So this is the formal statement of the Johnson-Linde-Strauss lemma, with the best known result in random projections. Given the matrix A, which is seen here as a set of columns in our M, and the set of columns is n columns, and some epsilon, which will control the approximation ratio. There is a k, which is now a little more precise. It's of the order of 1 over epsilon squared times logarithm of n, and a k times m matrix T, which is our projector, okay, such that the following happens. As you can see, the L2 distance between projected columns is sandwiched between 1 minus epsilon and 1 plus epsilon of the original distance, well, of the L2 distance of the original columns. Okay, so this is how the JLL presents itself. Now, the proof of the JLL, I'll dispense with it because I won't have time, but what happens is that you prove, it's a probabilistic method proof. So you prove that A and TA, that was a black matrix TA, the probability that they are approximately congruent exceeds some positive value. Okay, so there must exist at least one matrix T that has this property. Okay, so in practice, though, this very low probability is not really an issue. First of all, you can resample T sufficiently many times so that you get, by union bound, you get as high a probability as you want. On the other hand, empirically, sampling just a few times will do. And in fact, I only ever sample once. So I sample once. I sample T. I just sample once, and then I use it, and then most of the times I'm lucky or I'm happy. Why does this happen? It's most because, in fact, this result here, that the average over all T's, that the L2 distance between the projected columns should be equal to the L2 distance between the original columns, is actually a deterministic statement. Okay, so the means project well. Now, the point is that you might have some standard deviation, some discrepancy from the mean. And all these random projections, they imply the use of some concentration of measure argument to show that these discrepancies are actually low. Okay, so why do I allow myself to sample just once? It's mostly because when you have big matrices such as the A matrix, where you don't know much of the structure, the chances are that there's also some errors in the data, and so it doesn't really matter whether you will get something wrong, because what you'll get wrong here in this guarantee statement is that for most of these pairs of vectors, the guarantee will hold, and maybe for a few, the guarantee won't hold. Okay, so this is how you fail to satisfy L. But it doesn't really matter, because in practice, if you're clustering the columns, a few distances that are not well maintained don't really change the whole result. Okay, most of the times. Okay, so another surprising fact is the case independent of the original number of dimensions m, which I find surprising because, well, you chose m because you thought it was correct to represent your data, but in fact it has nothing to do with representing the distances. Which only depends on the number of columns, okay, not the number of features. So the realm of application of random projections is actually data, as I presented the theory. So I've tested, for example, a clustering of a few images, and you can see that it took me 0.4 seconds to obtain this answer. But when I projected the vectors representing these images, I obtained the very same clustering with only a fraction of the time. So this is where random projections come in very useful. Okay, so they reduce the time for performing certain operations on data. Now, the fact that I had exactly the same answer, well, that was lucky. Maybe I might have slightly different answers, but not very different answers. If I wanted to have perfect answers or almost perfect answers, I would have to tune the epsilon carefully, and I would have to sample my random projections several times until the probability of failure is very low. All right, but let's see now the focus of my work. It's in projecting formulations. Now, projecting data and projecting formulations are completely different things. Okay, so whereas in projecting data we might want to really just ensure the L2 distances, in projecting formulations we want to ensure approximate feasibility and approximate optimality. We also want to retrieve a solution for the original MP. We're not happy with just finding the optimal and approximately optimal value, or the fact that some infeasible problem projects with high probability to an infeasible projected problem. We also want to retrieve a solution in case the problem is feasible. And this may be easy in some cases, but hard in other cases, as we'll see. The two technical difficulties that I've had to face in bringing these data projection techniques to formulations is the fact that approximate congruence does not trivially imply approximate optimality. The objective functions can be anything. They can be linear, they can be quadratic. We've tested a few. We've worked out theories for a few mathematical programming paradigms. And it's always a challenge to transfer a result like the JLL to feasibility and optimality. And the other big challenge is that the JLL projects finite point sets. So I've specified that the A object is either a set element or a matrix with n columns, but it can't be an infinite point set. Okay, so the JLL would not hold with infinite point sets. There are some results similar to the JLL for those cases, but the JLL will not hold. Okay, whereas if you want to project something, if you want something like a formulation, there are decision variables, there are symbols that represent or may represent infinite sets. So in fact, there's an inherent difficulty in passing from data to formulations, and those are the decision variables. They represent the output of the problem, which you don't know yet, so it's not data. Okay, it's the possibility of data. It's the possibility of assigning values to the vectors, to the variable decision variables. So far we've dealt with LP, linear programming, SDP and conic programming in general, QP with linear constraints, QP with one non-linear constraint, with one quadratic constraint, which is like a ball constraint, and then a single problem, but the K-means problem. So this is not a paradigm. This is not like, I don't know, MI-NLP. But the K-means problem turns out to be an MI-NLP. So I'm quite happy that this, I could finally reach the stage where I projected something that has an integer variable in. But of course, most of the theoretical work was in continuous optimization. I'm saying of course because in fact it's something that concerns me. I still don't know how to project integer variables. With continuous variables, it's easier, probably because you can see the projection technique was an inherently continuous one. Okay, so it doesn't matter if A contains zeros and ones. Once you multiply it by t, it will contain anything. All right. So let's look at linear programming first. And first of all, let's look at linear feasibility. Okay, so we're going to just look at ax equals to b, subject to some other constraints that we're going to call big X. Okay, and for example, the linear feasibility problem would have x equals the non-negative orthant. Integer feasibility would have this kind of definition. Okay, so if x is finite, we have this theorem, which is probably the easiest theorem that I can prove to you, and maybe it will stay the only theorem that I prove to you today. But I want to go into the details here because it shows you how you deal with these things. Okay, so if x is finite, everything is easier, exactly because the JLL deals with finite sets. But let's look at this. So first of all, T is a JLL random projection, and B A1 to AN are the data of the restricted linear membership instance. So A1 to AN would be the columns of A, and B would be the right-hand side. And we want to show whether B is actually e to AX whenever X ranges in big X. Okay. So the first statement is trivial, and it says that if your problem is feasible, okay, so if the feasibility problem is a yes instance, then the projected feasibility problem, where you pre-multiply both sides of the equation by t, by linearity of the linear operator t, of course, this is also feasible. So this very important result, although it's trivial to show, says that if you have a feasible LP, okay, and you pre-multiply the equations by t, okay, and you get something like this, then what you obtain, the projected linear feasibility instance you obtain, is also feasible. So if one is feasible, the other is feasible. Now, number 2 says something different. It talks about the certificate. Supposing that X is not a good certificate for the feasibility instance, then the probability that X is a good a good certificate for the projected feasibility instance is low. Okay, in fact, I've written the contrapositive here. The probability that X is not a good certificate for this linear feasibility instance exceeds 1 minus something that decreases exponentially really fast. So this is a WAP kind of result. And this is an immediate application of the JLL, because you can look at the set of vectors B, A1 up to AN, and you can simply look at the distance between B and the other term, okay, X T A I. Okay, so this distance projects, and if there is a difference here, then this distance is greater than 0 in the original space. And that means that in the projected space, the same also follows. Okay, so this is a straightforward corollary of the JLL. Now let's look at the number 3, which is the one where we do a little more work, but not very much. Now suppose that that X is finite, okay, and now that the original problem is actually infeasible. So for every Y in big X, you never satisfy the constraints, okay? Then we can use the union bound on part 2, and if you don't know what the union bound is, go look it up. It's a very, very basic technique for dealing with probability for probable events. Then the probability that for every Y the projected instance is infeasible has the same kind of form as number 2. You can see that the difference here is that the cardinality of X got put into the factor of the falling exponential. Okay, so this is a typical effect of the union bound. The conclusion is that this kind of thing is WAP as long as the cardinality of x is not too large. Okay, so for example, if the cardinality of x were infinite, then this statement would make no sense. If the cardinality of x were increasing exponentially with k, then this would be maybe a high probability. So it wouldn't tell us that it's WAP. It wouldn't tell us that it's a full, that, you know, the probability of achieving this quickly goes to 1. All right. So this is the kind of statements and proofs that are involved in working with random projections. Okay. So look at, yes.
We have a question. If you don't mind to take a question.
Sure. No, I don't.
Wolfram, would you like to state your question yourself? He was asking whether the normality is an assumption.
Whether normality is an assumption?
Wolfram, do you want to unmute and ask your question?
Can you hear me now?
Yes,
yes,
we can hear you.
Sorry, I was muted. Somebody muted me. Now I see that you can even see me here with my video. Okay, good. Sorry. Leo, I have the question. When you write about probability, yeah, you are talking about your random projections. That means you are talking about your assumption that you made on slide 1 or 2, where you had this projection of size normal 0, 1 over square root of k, right? And I was wondering how sensitive, whatever you are talking about now, how sensitive it is to this, say, sub-Gaussian or assumption. So this is nice theory, I agree with that, but is it really so that I can legally ask the question, what about fatter tails? How do your probability bounds look like when you have slightly fatter tails? Say exponential, yeah, not normal.
I don't know. I don't know. There are some studies in there. You can look at the book by Vershinin. So I'm sort of taking the material from random projections, really the classical ones that are sampled sub-Gaussian in a sub-Gaussian way, and applying them with the basic machinery. But I don't know how far you can push, you know, the sampling with other distributions.
Okay, good. So may I then say this is very good for, say, phenomena that I can see in TA space that are typically linear. Can I say that? Because normality tends to essentially extract principal components in the end of the day. Yeah? If you want to say so, if you hit the principal components with T, you are fantastic. Then you find everything super. I mean, maybe this goes too far, this question. I just wanted to know how the probability bounds will depend on if you are less thin tails. Yeah, that's what I wanted to know. And
yeah, I don't know how to answer the question, in fact, but I can refer you to this book by Vershinin, which is just behind my screen. Maybe I can take it out of my. Okay, so this one is a very nice. Okay, can you see it?
Yeah, sure.
Yeah. All right. Okay.
Thank
now,
you very much, Leo.
No problem. Thank you for the question. All right. So let's go back. Okay, so this theorem doesn't quite settle linear programming, because in linear programming, big X is going to be uncountable. Okay. However, we are able to also project separating hyperplanes. So we've seen that the real issue is not feasibility. If your LP is feasible, the application of the matrix T will make the projected problem feasible. So we focus on infeasibility. Okay. So, and we take one of the alternatives of Farkas lemma, the one that says that if it's not feasible, then you can separate. There's a separating hyperplane, and we show that we can project. This is another easy proof, but I won't have time to go into it. You can project the separating hyperplane, and what you obtain is from this then you obtain that, which is exactly what you wanted to obtain, and similarly for the other projected vectors. Okay, so as soon as you can prove a theorem like this, then linear programming is, well, linear feasibility is kind of done. In fact, this is not what we do. We've proved the theorem with more difficulties, but that gave us a better approximation. And so this is not exactly what you'll find in the math of our paper. On the other hand, I think that the full statement of the linear feasibility projection theorem says, given a delta, and look at what I'm doing here. I'm no longer using the WAP kind of statement. I'm sort of giving myself how close I want to be to 1. Then given this delta, so given my precision in probability, there exists sufficiently large M and N such that for any feasibility inputs A and B, where A is N times N, we can sample a random K times M matrix with A's much smaller than M, so that if original LFP is feasible, then the projected LFP is feasible, and vice versa. And of course, the vice versa is the difficult part of the theorem. Okay, so now the optimality projection theorem is going to exploit the feasibility projection theorem, at least in my slides, because I only have time for sketching, whereas in the paper it doesn't really do that. It proves things anew. On the other hand, so let's look at the optimality projection theorem. We have the original problem here and the projected problem here. You can see that here we're projecting constraints. We're not really projecting variables, so we have fewer equality constraints. We assume that P is feasible and bounded, and we assume that all of the optima of P satisfy this boundedness condition. Okay, and so we can prove that given a delta, this delta is not exactly the same as this delta. This is not a precision probability. This is a precision in value. So value of P minus delta, and the value of P sandwich the value of the projected problem. Okay, there are some more conditions on this delta, unfortunately, which makes this this precision not really controllable a priori. Okay, so this is like a quality statement more than a quantity statement. The proof sketch, well, if you look, one side is really easy. You just realize that in fact the projected problem is a relaxation of the original problem because you are aggregating constraints. Okay, that's all. And for the other direction, in fact, you turn optimality into feasibility by writing a constraint instead of an objective function, and say that Cx is equal to the value of P minus delta. Okay, of course, if you choose delta greater than 0, this is going to be infeasible. Okay, because there are no values that are that have objective value less the optimal one, less than the optimal one. And so you can apply the infeasibility projection theorem, and then you just turn things around, and out pops what you wanted to have. Now, in fact, it's very easy to prove that the solutions of TP, of the projected problem, are actually feasible in P with 0 probability. So they're almost never feasible in P. Okay, so we need a different method to retrieve the original solution, and what we've devised is an approximate method. We extract, of course, we want to solve TP. We don't want to solve P, okay, because this is the whole point. We want to solve the projected one and find the solution of the original one. Okay, so we can extract from the solver the optimal basis of TP, and then this basis H has cardinality K. So AH, the columns of A corresponding to this basis, make a tall and slim matrix. M times K is tall and slim. So we can solve the K times K system, which is a pseudo inverse here technique. A transpose H, AH, XH equals A transpose HB. Okay, so we find a solution XH which only concerns very few components. Okay, but then we pad X with zeros. We make up X by XH and all zeros, and we prove that there's a small feasibility error with arbitrarily high probability. Now, this kind of assures that you're going to have AX equals to B. So unfortunately, the small feasibility error is going to be observed into the only other constraints possible, that are these ones. So we obtain original solutions that are slightly negative, which is bizarre for somebody who does optimization, because you wouldn't think, you might accept some infeasibility here, but you would never accept, I don't know, that you need to put a negative quantity of a certain number of food or nutrients to ensure something, to ensure a diet. So it's something that is not exactly so pleasing, okay, but this is the result we have. So these are infeasible random instances, and the whole game here is to observe how many wrong classifications we make, how many times we solve a projected instance, and in fact the original the original was infeasible, but the projected is feasible. Okay, so this is the only thing we count, and you can see that wrong is always at 0. Now 0.0 doesn't mean 0. There may be some 0.000 and then something, because we've tested many instances, but in fact it reduces to, you know, this technique working most of the times. Okay. As for feasible random instances, we picked an epsilon at 0.2, and this is an empirical choice. And you can observe that the CPU time is in favor of the original problem when the problem is small, because it takes time to project and then to retrieve the solution. So the CPU T is really the CPU in order to not just to solve the projected problem, but to go from the original problem to an original solution by means of the projected problem. So there's the projection, the sampling, the projection, the solution of the projected problem, and then the retrieval. Okay. Now you can see that this is slower, but then when the big sizes kick in, you can see that the CPU time is in favor of projecting. And now the negativity error, you can see that it's non-zero, but it's got this nice feature that is that this average negativity error decreases. Okay, so this is not too bad. And this objective error is really the cost error. You can see this here, and we want it to be close to 0, and in fact it is rather close to 0, so we're doing well. Now let's look at conic programming. Now, in order to extend our work on linear programming, we use the concept of a Jordan algebra. My introduction to Jordan algebras today will be very limited, but it's a formal abstraction of all of the nice self-control cones that we use in mathematical programming. And the point is that you can construct eigenvalues in an abstract way and prove a spectral theorem in an abstract way. And this is all that really takes to talk about cones, it turns out. Okay, so a real algebra is a vector space over R with an abstract product, and so you can sort of take products between vectors, so you can have a vector squared. Okay, it also has some other properties which I'm not going to use in these slides. Some examples, for example, if you want to take the non-negative orthant in Rn, so the useful LP paradigm, you can use the component-wise product between vectors. If you want to look at SOCP, you have this other product, okay, where you write a vector in Rn plus 1, like A0 and then A bar, and the bar would be A1 up to AN. And the first component of the vector is the inner product between the bars, so A bar and B bar. And the other components are A0 times B bar plus B0 times A bar. This is weird, but it works. And for real symmetric matrices, use this commutator, which gives you the SDP. Okay, so in fact, the construction works as follows. First of all, given a vector A in the algebra, you can work out the degree as the largest R, such that 1 A squared up to AR are linearly independent over the vector space. Okay, so this gives you the degree of A. The polynomials are constructed by means of plus and the times, the multiplication by between vectors. Eigenvalues are defined by minimal polynomials, and the spectrum, as a completely abstract spectral theorem, can be proved. As you can see, for every element of the algebra, you can find some values, lambda 1 to lambda r, and some vectors C1 to CR in the algebra itself, such that you can write A in terms of the eigenvalues and the eigenvectors, and you also have these sort of orthogonal properties between the vectors. Okay, Now, the trace can be defined by sum of eigenvalues. The inner product in function of the trace induces a norm in the algebra. And now the positive semi-definiteness is given by the fact that there exists a B such that A is equal to B squared. Okay, so this is how you construct all of the concepts that are used in improving, you know, programming over a cone. Okay, so this construction is due to many people in the past, but I think that Farid Alizadeh wrote a nice introduction as a chapter of a book. Okay, so in order to project conic programs, we write the primal and the dual here. And in fact, we make these two assumptions, which we already made for LP. Feasible instances are explicitly bounded by theta, and we also need strong duality on the cone programs. This is not an issue in linear programming, but it's an issue in SOCP and SDP. All right. Now we again project the constraints. So as you can see, this is where T happens to be. The dual sees T creep in the objective function. And I'm not going to say much about the techniques used here. But in fact, the feasibility and optimality guarantees end up using this additive error term, which is not ideal because, again, it uses the dual solution. So it's not a great guarantee, and the solution retrieval is very similar to what we do in LP. Okay, and the proof is a little different. In fact, the proofs of these things, I think they are clearer than the proofs in the LP case because they are forced to be more abstract. Okay, mathematically speaking, they are clearer. Okay, so let's see how this performs. The tests on infeasible random SDPs, they are very successful. Success rate is 100% if epsilon is kept low enough. If I increase epsilon, I start to lose resolution, okay, and I get some errors. And if I get up to 0.2, nothing. So all of the infeasible original problems would project to feasible projected problems. So there's an art to this deciding epsilon. Unfortunately, it's not a science; it's an art. Okay, the tests on feasible random LPs, they are both good and bad. In a certain sense, they are bad because you can see that this error of happening between the error measuring the value of P and the value of the projected problem is quite high. So there's a big difference. On the other hand, once we retrieve the solution, X tilde, the retrieved solution performs really well and has an error of 0. So in this case, although the projected problem doesn't give you a good evaluation of the objective function, of the optimal objective function value with respect to the original problem, for some reasons the retrieved solution works extremely well. Okay, and well, the CPU time, of course, decreases, but this we expect. So let's switch to quadratic programming. I'm going really fast because I don't have much time. So this is the formulation I'm using. And in this particular part of the talk, we will see that the projection is not applied to the constraints. In quadratic programming, with these inequality constraints, we're going to project the variables instead. Okay, so we start from this formulation where the t's are scattered about in a certain way in order to make the dimensionality fit. But what is happening here is that we're replacing x by t times x. Okay, so we are multiplying a vector of decision variables by a matrix T. And this is not exactly what should happen in the Johnson-Linde-Strauss lemma, according to the Johnson-Linde-Strauss lemma. So in fact, our proofs are more complicated here in this paper because we have to take account of this, okay, of this fact. We're doing something that doesn't immediately translate to the mechanisms that make the JLL work. Okay, so anyway, we set u equals to t of x, and this is what we obtain. We obtain something with fewer variables, okay, because we know that this t is k times n and x is n, so this is only k, and k is logarithm of n. Okay, so now we simply replace this big matrix by something else, by another name. We're just renaming things so that it's easier to recognize that what you obtain in the end is simply another QP. Okay, so this is the same as this. So it's another QP, but with smaller sizes. Okay, so n has become k, and k is proportional to the logarithm of n. The solution retrieval in this case is trivial. Okay, so there's no problem. Oh, by the way, I'm not going into many details, but I'm going to send the slides to Dolores, and you can look at the details later on. The approximation results here assume certain things, boundedness like usually. We also assume that we know a circumscribing sphere centered at the origin that contains the feasible region with radius r. So we define two problems, two projective problems. This one, which is t times p, which we've already seen, and this tp epsilon, where we make the constraints tighter, okay, by adding a constant on the left-hand side. So these two will sandwich the results, in fact, and this is what we obtain. The optimality theorem that we obtain is this one here. You can see that val of p is sandwiched between tp and tp epsilon plus eta. Unfortunately, eta is not really great, and we didn't find any way to improve this this very slack error. We tried then to sort of convince the readers of our papers that TP and TP epsilon weren't too far apart, okay? Because if this were at minus infinity and this at plus infinity, we wouldn't have proved anything interesting, okay? So we tried to convince the reader that val TP epsilon and val TP were not too far apart, and so we proved these two other theorems, one which said, multiplicatively speaking, we are not too far apart, and the other that said, even additively speaking, we are not too far apart, okay? And unfortunately, again, this sigma and this E, they are not great, okay? In fact, we've had to transform multiplicative distortions into additive distortions, and these are sort of the tools of the basic lemma that we've used over and over again in the paper. You can see that somehow this says that the angles between tx and ty is more or less like the angle xy plus or minus some tolerance proportional to x and y, and this talks about linear expressions, and this talks about quadratic expressions, okay? So using these three lemmas, we've managed to put together a theorem that talks about the whole QP. Now, if you set Q to 0, of course, all the results go through. What you get is a projection for the LP in canonical form. And this is the projected version, and in fact this is the dual to the original projection that we've already talked about before. Okay, so these two theories provides two different arrival points to show that you can project LPs in standard form and LPs in canonical form. In the one case, in the standard form, you project the constraints, and in the canonical form, you project the variables. Okay, so I'm not going to go into too many details for the tests here, but essentially I've generated a lot of random QPs, and the results were not great in the sense that, yes, you know, increasing the size doesn't yield a linear or quadratic increase in the complexity of solving or the quality even of the performance quality of solving the projected problems. It's slightly better. I mean, it seems to be sort of either a square root or a logarithm. What I would have liked to see would really have been something like this. Unfortunately, in QPs, we didn't get this. And so these are empirical results, which means that somehow QPs have either we're not projecting correctly, either there is some scaling factor on the objective function that we have not hit upon, which may well be the case, or else these techniques are not really so great for QPs. They're not bad either, but they're not so great. And the last thing that I want to talk about in the theoretical part would be the Kmeans MINLP. So the Kmeans problem, everyone I think knows it. Given points in our M, find clusters. such that each point is closest to the centroid of the cluster it belongs in. Okay, so it gives rise to a very popular heuristic called the Kmeans algorithm. And why should we want to bother with modeling with an MP? Well, because sometimes you have side constraints that no one has really treated with K-means, and in that case, your best hope, not to waste too much time, is to whip up a mathematical programming formulation and add the side constraints. So this is an MINLP formulation for the K-means problem. You can see that I'm defining a centroid with variables yj's, and this is the obvious objective function, and these are binary variables that assign a point to a centroid. Okay, this says that this is a partition, and this is the cardinality of each cluster. Okay, so this can be yes.
Fabio had a comment.
Yes.
Yeah, so he mentions that K-means is just a heuristic.
Yes. It's
Leo, just you mentioned the K-means algorithm. Okay, there are good reasons for doing something else, because K-means just give you a local optimum, not a global one.
Sure, I did mention that it's a heuristic called the K-means algorithm. There's also some approximation algorithms based on K-means. So it's not only a heuristic, or maybe it's a heuristic that people have studied, and some people have managed to prove certain approximation results. So it has a status that is slightly more reassuring than any heuristic. On the other hand, it is frighteningly fast and obtains very good optima in many cases. So somehow it's one of those heuristics that you want to keep in your closet, or maybe no, in your drawers, so for ready use. Okay, so thank you, Fabio, for the comment. Back to the formulations. In fact, you can easily reformulate some of the things that you see here. For example, you can see an objective that is almost convex, in the sense that there's a variable multiplying, 0, 1 variable multiplying the rest of the term here, but it's easy to reformulate this using McCormick constraints, and this is what you obtain. Actually, not yet McCormick's. I'm just sort of replacing the convex part by an added variable, big P. Okay, and now this is a reformulation of the centroid definition constraint. And also I note that every continuous variable, in fact, can be bounded above and below. Okay, so now you're in the situation where you have binary times continuous bounded variables, which is also very easy to reformulate using McCormick constraints this time, or Forte McCormick. And what you obtain is a convex MINLP here. Okay, you can do better than convex if you're willing to approximate these constraints by means of other norms and obtain approximate reformulations, of course. But even a CMINLP is not that bad with respect to the non-convex MINLP as we had before. Now, here you can apply random projections in this way by inserting in these projections before the data. Unfortunately, here you have to insert it before a decision variable, which of course matters, as I explained before. But this technique yields smaller CMINLP for approximations, and you can get the solutions faster. I'm not presenting any results for this application, but you can go look at the paper if you're interested. All right, so the theoretical contribution of this paper has been that we've identified what we think is a hole in the proof of another paper that sort of proved what we needed, and we fixed it. Okay, we fixed it by introducing a completely different technique, meaning additive JLL, but it'll be for another talk maybe. Okay, so case studies. I'm going to maybe spend 5 minutes in this, and then there'll be 5 minutes left for questions. Okay, so diet problem, quantile regression, compressed sensing, and portfolio optimization. I don't think I'll get to the end of this, but let's look at the diet problem. Everybody knows the diet problem. This is it. Okay, these are the constraints. Of course, we want a standard form. That's not quite standard form, so we can simply introduce slack variables and use a different constraint matrix. And now let's look at the results. This is a first instance with very few nutrients and very few foods, but we get exactly the same cost and exactly the same solution. And this is not retrieved solution. Really, the projected solution is exactly the same as the original solution. Okay, zero error. Now, if we increase and we look at a single instance 2000 by 100, we get this dependency between the epsilon of the JLL and the precision of the solution. Okay, you can see that you can increase the epsilon by a lot, and since the epsilon controls how large k is, okay, so we started from 2000 constraints, and with 0, 1 we get 765 constraints in the projected formulations. With 0, 2 we get 191, and now we can go down up to 16 constraints. This is an aggregation of all of the original constraints, random aggregation, and just 16 constraints are enough to retrieve exactly the same solution. Okay, and then suddenly there's a phase transition here, there's a phase transition effect, and suddenly you get an error, and the error is large. With larger instances, for example, I had to locate epsilon sort of by hand in all three cases, but I was able to pinpoint you know, the least epsilon where you would retrieve exactly the same solution, and all infeasibility errors were null. Okay, of course there's a CPU time saving in every case, so that's not bad. So for the diet problem seems to be a large success here. Quantile regression, well, quantile regression is similar to linear. This is a linear regression, and quantile regression is not too far from it. It can be modeled by an LP, and this LP has a shape that is usually as follows. It's got a dense part and then two diagonals. Okay, so again, a test. I run more than one test, but I'm showing you here one test on a set of electrical prices database. And this is the original problem, and this is the projected problem. These are the solutions. You can see that they're more or less the same, aside from a certain discrepancies. This and this, for example. And then I found out that these discrepancies came about because these are European countries, and from a certain point onwards, they all had the same prices. Okay, so these are simply permutations that apply because some of the data were exactly the same. There was also another bigger instances where I was also able to show a time saving. Okay, so in compressed sensing, in fact, I have to spare you all of the details here, but in short, you have to solve an LP such as this one here, okay, which is a reformulation of this program there, okay, and it's used for signal processing. Okay, solving this LP is this is a well-studied LP, so many things are understood about the random behavior with random data of these LPs. Okay, but I did find somehow that I was able to sort of exceed the expected precisions of these basis pursuit LPs, and so I was able to send and retrieve a message using a linear code in a perfect way using much less CPU time. Okay, you can see the projected LP and the original LP. Portfolio optimization is a straightforward application of the QP material, but in fact we used also some other constraint. Well, we used a sort of a different formulation of portfolio. This is not the pure Markowitz. You can see, for instance, that you've got a maximization of the expected return minus the risk. So this is a scalarization, and you can see that there are some budget constraints for certain categories of stocks, and that you can have short sales, so you can have negative variables. Okay, so this was sort of to fill the setting of to better fill the setting of our QP work. And again, this, you can see that it sort of belongs like the QP work that we've seen before, in two true data sets here. With this particular formulation, which was slightly different from the one above, we can get some interesting objective function ratios here, but we have feasibility errors. So it's not perfect. Okay, so this takes me to 5:25. There's 5 minutes for questions. This is a list of my papers, but please go look also at to other people's papers. For example, Correia Cartis has some papers in Out and also in Archive concerning random projections for optimization. Thank you very much.
Thank you very much, Leo. So if you have a question, could you please raise the hand and we will give you the voice.
I can't see anything as usual, but never mind. Tell me, okay?
Yeah. Yeah. So Emilio has a question.
Hi, Leo. This is not a technical, but a philosophical question. How far can you think we can go with random projections in order to reduce dimensionality in the challenging problems in practice many people are facing right now?
Okay. I don't know. I think that if you have a lot of data, your data may well have both structured and unstructured parts. And because of this, they may be amenable to some application of random projections. Maybe you have to separate certain set of very ordered constraints from certain others and only apply the random projections to the others. But it really depends on the kind of structures of the. I've observed, for example, that if you have a constraint matrix that is part dense and part very sparse, these projections work well. On the other hand, for example, you've seen the results from QP. Those results are not really the best that I could hope for. And it's not a question of theory. It's a question of empirical tests. So how far can we go in practical matters? Well, I've worked on a project by RTE, Réseau Distribution Transport d'électricité. So this is the big cables, you know, the cables that carry, I don't know, 20,000 volts across the country. And they wanted to solve a certain problem connected with the forecast of quantity and wind. Okay, so quantity of electricity produced with wind, and so they had a quantile regression problem, and we solved it, and it was fantastic. It was an excellent reconstruction of the original problem. But then, you know, for some other structures, it just doesn't work well. Or especially if there are integer variables, I still don't know how it works. I mean, I have some sort of tests with no theory behind that shows that it works reasonably well. And then I have some other tests that shows nothing at all. So I don't know. I think that there's some hope to use them in practice, and some people have used them in practice. But I think that it really depends on the structure of the problem itself.
Thank you very much, Leo.
You're welcome.
Hughes, you had a Eddie Hughes?
Sure.
If not, I can.
Can see me?
Yes, we can see you and we can hear you.
Okay, yeah, very nice story, Leo. That's what I said. It was a bit surprising to me that you were going into stochastic things. So
I know.
I trust Fabio completely on this. One of the counterintuitive things for me in the beginning was that you focus on random directions from a normal distribution. But my intuition says, wouldn't it be logical to use only positive directions? That means you sample of the unit simplex, for instance. You can do that by negative exponentially drawn and normalizing, and then you only go in the positive in the positive sense. Let's say it like that.
Okay, but that has an issue, meaning that you can't. I don't know if you can really go back to where I was. Let's see. View mode, thumbnails. Okay, let's see if I can go quickly up. So it would sort of destroy the theory at this point. Let me get it here. Okay, so this would fail to hold, and this is the sort of the cornerstone of all of all of my theory. So if you used any distribution without zero mean, this result would not hold. I'm sorry. Okay.
I have some
Yes,
background noise. Don't worry.
Oh, okay. All right. Did you
He must have
hear me?
some
Did you
background
understand?
noise. Yeah. I got the point.
Okay, so anyway, Eligius, it would be great if I could use any distribution I wanted, but I can't. At least I'm not able to. Okay, so for the time being, I need zero mean distributions with rapidly falling tails.
Thank you very much, Leo. Is there any other question? I'm checking at the chat, and yeah. So there don't seem to be any other questions. That was very interesting talk, and lots of
Finally, I can see.
good, lots of good results to reduce dimensionality.
Thank you.
Thank you so much for coming today and giving such a thorough
Thank you for the
presentation.
invitation. Very grateful.
Yeah, and we see each other next week with the presentation of Cornelia Curtis. Thank you, everybody.
Bye. Bye. Bye.
Bye. Thank you, Leo.
Bye.
Bye.
Thank you. Bye. Bye. Bye.